Today I'm going to look at how halogenalkanes or haloalkanes react. If I take bromoethane, for example, and I reflux it with aqueous sodium hydroxide, I will make ethanol. So on my arrow here I can write the reagents and conditions. So sodium hydroxide, aqueous, so that's the reagent, and the conditions are reflux. And essentially we can see here that the halogen, the bromine in this particular case, has been substituted for an OH group, hence forming an alcohol. The name of this particular mechanism is nucleophilic substitution. So nucleophilic, 1L, substitution. Substitution, well, we've already seen because we're swapping the Br for the OH. Nucleophilic, well, this reaction involves nucleophiles, and the hydroxide ions from the sodium hydroxide are going to behave as a nucleophile. What is a nucleophile? Well, a nucleophile is a species with a negative charge or a lone pair of electrons that can be donated to form a covalent bond with a positive or partially positive carbon atom. I've written this definition out in full because you need to do the same. You need to put it onto a flashcard and add it to your Rolodeck, and you need to learn your definitions. It makes life so much easier as we move through this A-level course. So common nucleophiles, well, obviously are negatively charged ions. We've seen hydroxide ion is going to behave as one. So there's my oxygen in a hydroxide ion. It's negatively charged because it's picked up an extra electron from somewhere. In the case of sodium hydroxide, that would be the sodium. Cyanide ions, this is an important nucleophile because it's a good way to add an extra carbon atom to a molecule to elongate our carbon skeleton. Nitrogen, of course, has a lone pair, but actually in a cyanide ion, negatively charged, so does the carbon. And it's this lone pair here that are going to be part of the reaction mechanism. The ions don't have to be negatively charged. We could be neutral molecules behaving as nucleophiles. As long as they've got a lone pair of electrons, they can donate. So ammonia is a good nucleophile, as is water, because the oxygen has two lone pairs, one of which it is able to donate to form a covalent bond. Let's look at this mechanism of nucleophilic substitution in a little bit more detail. I've pre-drawn out my bromoethane in 3D, primarily because I can't draw in 3D for the life of me. So here goes. My nucleophile, well, in this case, I have chosen it to be the hydroxide ion, so I'm drawing it OH. I am going to draw in the lone pair of electrons and the negative charge. I only need to draw in one lone pair, the lone pair that's going to make a bond with the carbon. Now, if we go back to our definition, this carbon atom is either positively charged or partially positive charged. Well, we know it's got a delta plus because it's bonded to bromine, and bromine is slightly more electronegative than carbon. However, as our hydroxide ion approaches, that's going to polarize this bond further. So the carbon is more partially positive than perhaps we might expect. Here comes our hydroxide ion. Now, drawing curly arrows denote the movement of a pair of electrons, and we need to be absolutely accurate at A level. So it starts at the lone pair of electrons and it finishes at the delta positive carbon. So many students don't pick up the marks for drawing out mechanisms, and this is a really common exam question, because they're just sloppy with the details. So always put in your delta plus and delta minus, your lone pair of electrons from your nucleophile, and we've drawn our curly arrows accurately. Okay, I'm just going to remove my little green arrows because otherwise it's just going to make life or my picture rather messy. What happens next? Well, simultaneously, at the same time as the hydroxide ion is attacking our delta positive carbon, bromine becomes a leaving group. And it's going to leave taking both the electrons out of the carbon-bromine bond. Again, I have drawn this arrow really accurately because the electrons are moving from the bond onto the bromine atom. Note that our nucleophile is attacking from the opposite side of the molecule from the halogen that is about to leave, and I'll explain why that's the case in a minute. So, these two things are happening simultaneously. We have, for a short period of time, a transition state. This is short-lived and it's unstable. And if I were drawing this in an exam, I would also put on my charges. So both the oxygen and the bromine are slightly negatively charged. And the partial positive charge is kind of spread out over the whole of this transition state. So I might like to put that on the outside of my brackets. Can we also note, while we're being accurate here, that the partial positive charge is on the oxygen. So draw it on the oxygen, not on the hydrogen, not in the general vicinity, but on the oxygen. So the transition state is very short-lived, and very quickly it falls into the product and the leaving group. So the bromine leaves as a bromide ion. It's taken that pair of electrons out of the carbon-bromine bond. The oxygen is now bonded to the carbon. Again, this is still going to be a polar bond because oxygen is considerably more electronegative than carbon. But it's also important to note, and this is the second reason why I've drawn this in 3D, that our product molecule, geometrically speaking, is inverted compared to my reactant. So if I scroll back, this was the geometry of my reactant, and we can think of it a bit like an umbrella. And in the product, we've got the opposite case, the opposite geometry. Our umbrella has been blown inside out. Now, 98% of the time, the fact that this happens is completely unimportant, except when our central carbon is chiral. And that will mean something to you when you get further along the A-level course. There's a very simple reason as to why our nucleophile attacks the delta positive carbon from the opposite side to where the halogen is. And it's simply because this incoming pair of electrons is going to be donated or deposited into or accepted into an empty molecular orbital on the carbon. And this empty molecular orbital just happens to be orientated along the carbon-halogen bond axis. So it would make no sense for our nucleophile to try an attack from a different angle because there is no empty orbital there ready to accept this pair of electrons and form the new carbon-oxygen covalent bond. Now, you'll be relieved to know that in an exam you would never be asked to draw this using 3D representations of our molecules. So I'm going to run through a second example using ammonia as a nucleophile in the way that we would draw it in an exam. So I am going from my reactant, which is bromoethane, to my product, in which case I have substituted the bromine for an amine group, NH2. The reactant in this case, or the reagent in this case, is concentrated ammonia, and the conditions, it's heated in a sealed tube. The bad news is that you need to learn all the reagents and conditions for each of the reactions that you look at throughout the organic chemistry section of A-level. So another good set of flashcards to be in the making of. Bromoethene. I have got carbon, hydrogen, hydrogen, methyl group, and the halogen. I've drawn it out simply because that's the way my brain works in terms of my incoming nucleophile. I find it easier to draw it from the right than the left. There's no other reason. I am going to put in my delta plus and delta minus. My nucleophile in this case is ammonia. I'm going to draw in the lone pair of electrons because this is what's forming the bond with the carbon. I'm going to be really clear with my curly arrow that it's running from the lone pair of electrons to that delta positive carbon, and simultaneously the bromine is going to leave, taking the pair of electrons out of the carbon-bromine bond. We don't need to draw the transition state, so let's move on to look at the product. Now, because the nucleophile has attacked in my picture from the right, the hydrogens and methyl kind of shuffle round. This would make more sense if it was in 3D, but maybe this is a good time to get out your Molly Mods and prove this to yourself. So I'm going to draw it like so, with the new bond to the nitrogen. And remember, this was ammonia. It's still got 3 hydrogens bonded to it, which means that the nitrogen is positively charged. It's lost its lone pair of electrons. It has an extra bond. It would like its lone pair of electrons back. So how is it going to do that? Well, it's going to kick out one of the hydrogens and take the bonding electrons back onto itself. So again, very careful with my curly arrow, moving from the lone pair of electrons onto the actual nitrogen. And so our final product, we are going to have carbon, hydrogen, hydrogen, methyl, the NH2 group, plus, well, we've kicked out a bromine and we've kicked out a hydrogen ion. So HBr is our byproduct in this case. And cunningly, we can see that because of the way I've drawn it, I have actually inverted my product, even though it's not in 3D. So, key points here. Firstly, make sure that you know and have learnt the reagents and reaction conditions for each of these organic reactions. Start yourself a series of flashcards and a big mind map. That would be really useful. Pin it to your bedroom wall, stick it on the ceiling so it's the last thing you see before you go to sleep at night. When we're drawing out our mechanism, then key things here are our delta plus, delta minus, our nucleophile with lone pairs of electrons shown, really accurate curly arrows, whether they're attacking a carbon or we're talking about an atom leaving. In the example here, our nucleophile was a neutral molecule, and this would be exactly the same if water were my nucleophile. I've got an extra step where I have to get rid of the positive charge on the nitrogen by kicking out a hydrogen. What to do next? Well, make sure that your notes are really clear and that you have all these exam tips and tricks in them. There is a link somewhere in the blurb to a PDF with the key diagrams here that you can download and annotate and add to your notes. Probably should have said that at the start, but hey. Now's the time to head over to the Crunch Chemistry website. There is a link in the blurb below, and you can find notes, exam tips and tricks, and sets of exam questions, everything you're going to need to help you get the grade that you deserve. If this has been helpful, then please hit the like button. Can't say that. Please hit the like button and press subscribe. It makes a huge difference to a small channel like us.